Today we want to talk about the fact that there's more to R3 than just surfaces and solids. What I mean is we've talked about double integrals in R3 and also triple integrals in R3. Our canonical examples, our primary examples that we use is that volume is area multiplied by height, or as we've written it here, height multiplied by area. So we're looking at some surface f of xy in R3, and we're trying to find the volume under the surface and above the region. This is the most direct extension of area under a curve and above an interval. It's still like all integration based on some multiplication. Here's height multiplied by area, and the region R, those are all the xy's that we're going to plug in to f of xy dA. But we're describing a function, function of two variables that's going to produce a surface in R3. And then R is just a region in the xy plane, representing all the stuff that we're plugging into the expression f of xy dA. When we talked about triple integrals, we still kind of kept our stuff in R3, although we could say this is a four-dimensional hypervolume. Let's keep it more grounded in something we can picture. W, that is the solid, or a solid in R3. So the W represents a solid in R3. It's a bunch of X, a bunch of Y, and a bunch of Z. And what we're doing is evaluating a function, some characteristic about that W that's continuously variable. And we want to add that value up all throughout the solid. So f of x, y, z could, for example, represent the density of the solid W at the point x, y, z. We multiply the density by the volume, dV, and find the mass of that little piece, and then add all those things up. So in the first example, in our double integral, we're in R3, and we're plugging in a bunch of x and y into f of xy dA. In the triple integral example, the W is a bunch of x, y, and z. It's a bunch of points that we're plugging into the expression f of x, y, z times dV. So in both cases, where the integral part is just, here's what we plug into the expression. R is a collection of points that we plug into the expression f of xy dA. W is just a bunch of points x, y, z that we plug into the expression x, y, z dA. This is one of the things that we've talked about in the past because it always comes up. The integral part is just telling you what to plug into the expression. It's just a bunch of points that you're plugging into the expression. The set over which we integrate, in these two cases, the R and the W, is just the points that we're going to be plugging into the expression that we're integrating. This is the read that we want to have on this. The R and W, those are just collections of points that we're going to be plugging into the expression that we're integrating. So that would be f of x, y, dA. And f of x, y, z dV. We're integrating over a surface, we're integrating over a solid. Now our surface, the region, the region that we're plugging in, that's in the XY plane. But it's still just a bunch of points in R3, xy, comma, 0. We see in the triple integral that W is just a bunch of X, Y, and Z. It's a collection of X, Y, and Z that we're going to be plugging into f of X, Y, Z times dV. We're integrating over a set, and that set is what we're plugging into the expression. Now, what we want to look at is how we're what kinds of sets we can grab from R3 to plug into some expression that we're presumably going to be integrating, because I mean, this is still calculus class after all. So that raises the question, what other collections of points from R3 might we want to plug into some expression? So that raises this question. What other collections of points from R3 might we want to plug into an expression that we're integrating? That's the trailer for what's coming next. We don't have exciting trailers in calculus. We just say, here's our next topic. No explosions or anything like that. I'm pretty sure that for most movies, for most modern movies, if you watch enough trailers, you'll see the movie. I know that's like such a basic thing to say, but I think it needs to be said. And the reason I like to point it out is because I'm pretty sure I remember the first time that they just started giving stuff away in the trailer. Rather than set up the movie and build anticipation, they just started showing big things from the trailer. The earliest one that I can see, that I can remember, and we should probably make a list of this stuff, is for the first Mission Impossible movie with Tom Cruise. So now, I don't want to spoil anything, but I'm going to be talking about what's in the trailer, so is that even possible? And number two, that movie is very, very old. There's a statute of limitations on spoilers. If you haven't seen it by now, you don't get to have a spoiler-free experience. Darth Vader is Luke's father. That's not a spoiler. If you haven't seen Empire Strikes Back by now, shit, you don't get to have that in the theater. You can't put the whole world, you can't put a gag order on the whole world to not talk about that element of Star Wars. You know what I mean? There's a statute of limitations on this shit. I'm not sure, but we're well past. That movie's from 1983. So that was a long, that's a great question. What is the statute of limitations on spoiling? Because stuff goes kind of blow through things really quick. Do you know what I mean? I don't know, according to the MCU and various actors in the MCU, it's like whenever we're doing the press junket for the movie that hasn't come out yet. Anyway, back to the original topic. Mission Impossible, it's a very old movie, and there's a very famous scene in the movie where there's a helicopter chasing a train through a tunnel, right? So I'm not spoiling it. That's just a fact. They show that in the fucking trailer. And then the helicopter blows up and Tom Cruise goes flying through from the explosion, flying through the air and landing on the train, right? And everybody's seen that because it's in the trailer. That's the big set piece for the fucking movie. That's the big climactic thing. That happens at near the end of the movie. It's at the end of the movie. It's the big thing, and they put it in the fucking trailer. Because they're trying to chase the thing, and the MacGuffin is getting away on the train. He's got to get on the train. Oh no, this guy was on my team, and he has betrayed us, and he's flying the helicopter. I'm going to blow up the helicopter and use the explosion to propel me onto the train. They put that in the trailer. It's a big dramatic moment. They put it in the trailer. And I think about that a lot because a little bit before that movie, there's this little small project called Jurassic Park. And the entire advertisement for Jurassic Park, the entire media buildup was a poster that had the Jurassic Park logo, the skeletal Tyrannosaurus Rex on the yellow background in the red circle. And it was just like all Jurassic Park, summer 1993. It's Spielberg and dinosaurs. That's pretty much what it was. They showed the picture of the dinosaur. They didn't say that, but it said the picture, it said, look, dinosaurs. Spielberg. Oh, summer 1993. It's like, oh, so there's a blockbuster with dinosaurs and Spielberg. And so, yeah, we're in. Then the other part of it was like a little cup of water going, right? Like the cup of water that jiggles. That was it. That's what you saw. These days, they would have just put the fucking T-Rex in the thing and had that the big glory shot at the end where the T-Rex is going, raw, and then like the thing when dinosaurs ruled the earth, right? They would have put that in the trailer these days. I'm convinced of it. Now, it doesn't matter as much now because one of the big reveals from 1993's Jurassic Park was looking at the dinosaurs and saying, wow, did they actually make dinosaurs for this shit? Because that's how visually impressive the movie was. But that's beside the point. Trailers for calculus class, not very exciting. Oh, good. Now that I've recorded all that, you can fast forward if you're watching on YouTube. Trick question. No one watches on YouTube. So the volume of the truncated sphere is still an active problem before we go on to this new set of points that we can plug into things that we're going to integrate. The volume of the truncated sphere that we had from yesterday, that problem didn't go away. I want to remind you that is still an active problem. It's still a question that I'm not answering. I do want to point out, I do want to remind you that you can find the volume of that solid using single variable calculus. Think in terms of solid of revolution. Go back to Calc 2. Set your Wayback Machine to Calc 2 when you're talking about solids of revolution, and find the volume of that truncated sphere as a solid of revolution. You can use washers, or you can use cylindrical shells. But finding the volume of the sphere, the truncated sphere, is not the problem. That's just a vehicle for the actual problem, which is write a triple integral. So remember, I'm not interested in what the volume of the sphere is. I'm interested in what a triple integral would look like that describes that solid. The good news is that you can use your single variable calculus skills to calculate what that volume is and then check that against the value that your triple integral delivers. So there's the good news. And this is why I assign problems that we can do with old techniques. Any questions? So I just want to make sure that you understand the assignment. It's about writing a triple integral, not about finding the particular volume. That's just a vehicle. You know what I mean? It's kind of like the movie Chef. I don't know if you've seen the movie Chef. It's a Jon Favreau movie. It's about a chef who buys a food truck, Essentially, that's it. But that movie is 100% not about a chef buying a food truck. That is the finding the volume part of the problem. Jon Favreau stepping away from the MCU for a film. That's the actual film. That's the point. You know what I mean? Ever see the difference? All right, let's talk about what the actual thing is that we want to talk about. What other collections of points in R3 might we want to plug into an expression that we're integrating? So far, we've had two-dimensional sets, kind of limited two-dimensional sets because we're picking points in the XY plane, and we've had three-dimensional sets. So I want to be able to plug in a one-dimensional set of points. So far, we've had three-dimensional sets. So this question of the types of sets that we want to plug into an expression that we're integrating. So far, we've talked about three-dimensional sets. That's the W in a triple integral. We've talked about two-dimensional sets in the XY plane. And so that gives us some other things that we want to talk about. So what if we wanted to integrate over some surface? That's one thing that we might want to do. Instead of plugging in a bunch of x, y into the function, what if that surface, what if that was the set of things that we want to plug in? We want to plug in the surface, not just a bunch of x, y from the surface. And what if we want to plug in a one-dimensional set of points? What if there's a path in three-dimensional space and we want to evaluate an expression at all the points on that path? What if we wanted to integrate over a one-dimensional path in R3? At that point, we'll pretty much have things covered as far as plugging in continuous sets in R3. In R3, we can have solids of three-dimensional solids. That is a collection of points. We can have two-dimensional surfaces as collections of points, or one-dimensional paths as collections of points. Remember what this game is about. The integration game is evaluating an expression at a bunch of points and adding up the results. Even though it's kind of fishy to say adding up the results, there's nowhere to put the plus signs because we're dealing with a continuum, but that's what this whole game is about. Any questions? Comments? In three-dimensional space, we get three-dimensional sets, two-dimensional sets, and one-dimensional sets. Suppose we have 0-dimensional sets, but then that's just like plugging in a single point, so not really an issue. And 4-dimensional sets, that's just too big. So we want to see this overall structure of what we're doing with integration. Here's an expression. Here's a bunch of points that we want to plug into that expression. So this raises some questions. We're going to start by looking at the 1-dimensional case. We have two major things to talk about here with this integration business. We need to talk about what if we have some set of 2-dimensional sets in R3 that we want to integrate over, but it's not just a bunch of points in the XY plane. It's not just a region from the XY plane, like we have with double integrals. Oh, now I've done it. And that once we have that, then we can integrate over 2-dimensional sets, all covered. We've already got triple integrals, which is integrating over 3-dimensional sets. Now we need to integrate over 1-dimensional sets in R3. So we want to talk about integrating over a path in R3. This requires two things. How do we describe the path? And what are we going to get out of this integration? How do we describe the path for the integral? That's a big part of our job in this double and triple integral business. How do we describe the set that we want to plug in so that the integral will understand what we're trying to do? Integrals just work like computers. We have to be very careful about how we talk to them because they are dumb and they don't understand. So first, how do we describe the path for the integral? And second of all, under what conditions might we want to do this? Clearly, this is a thing that we want to do. Under what conditions? What will this tell us? What's our canonical example going to be? For single variable definite integrals, our canonical example is the area under a curve. We upgrade that to functions of 2 variables when we want to find the volume under a surface and above a region. In a triple integral, one of our favorite examples is find the mass over a solid with variable density. So what is integrating over a 1-dimensional curve going to tell us? What's our canonical example? How's everybody okay? Spend a lot of time on setup and trailer, but I want this to be in context. Mostly because I think a lot of times we get into these patterns in math classes, especially. It's like, here's a thing that you can do. And then people are like, oh, when am I ever going to do this? And no one wants to say, well, like this specifically, like factoring polynomials, probably never. But that's not the point. And students are like, oh, dude, you said probably never. So My motivation is out. So then we put up all these weird ass applications, these super contrived applications that make you do the thing. And I think as teachers, we don't realize like the contrived example is still does not answer the question, when am I ever going to do this? But like I said, doing the thing is not the point. Understanding how we think about things, that's the point. And it's generally, as a teacher, it's considered unprofessional when students are like, oh, why do I need to know this? To be like, oh, I guess you don't, get out. Or remind you that you volunteered for this. You tell me. But I don't like doing it that way either, because that's just blaming students for being in the position that we collectively put you. So here's going to be the first thing that we need to be able to deal with. We need to be able to describe a path in R3. And here's one of the ways that we're going to describe a path in R3. Now, parameterized curves is not necessarily a new thing, but it's not necessarily an old thing. So we can kind of put this in the category of recall. But it's a little messed up to do that because some of you might have had a trig class where one time you talked about parameterized curves. And then in pre-calculus, maybe you talked about parameterized curves. And then in calculus 1 and calculus 2, maybe you spent like 1 or 2 days collectively talking about parameterized curves. So let's talk about parameterized curves. So the idea here with parameterized curves is that instead of making one variable a function of the other variable, or writing an equation where the two or three variables depend on each other, we're going to define the variables independently of each other and make them functions of some other parameter. So the big idea in parameterized curves is, rather than make the variables depend on each other, either through a function or equation, So rather than defining a curve by relating, this sentence just did not come out. It got rewritten in my mind. Rather than define curves by a function or relation in which the variables are defined, the curve is defined by the relationship between the variables. So rather than define the curves by function or equation, that is a relationship among the variables, we define each variable in terms of some other parameter. So the idea here is rather than make a relationship between x and y and establishing a curve that way, we make x and y functions of some other parameter. So I'm going to use our favorite example, a circle, or in the case of the function, a half circle. X and y are not functions of each other. They're functions of some outside parameter. T is just there. T has been installed by us to make the curve where we can define x and y independently of each other. Now x can do its own thing and y can do its own thing, and they don't have to depend on each other. T is not some actual location that we're trying to describe. And that way, T is sitting outside the space. X and Y are our locations, and then T sits outside of that. Since I'm not requiring that the variables depend on each other, if I want to say build a parameterized curve, describe a parameterized curve in R3, I just have some function for x, some function for y, and some third function for z. If I want to describe a one-dimensional curve in R4, I can describe a function of x, a function of y, a function of z, and a function of z2. And we're not going to be restricted by requiring a relationship between our locations. Any questions? All right, so this is going to be our next big thing. We want to learn how to parameterize curves, or we want to remind ourselves how to parameterize curves, one of those two things. And then we want to expand it to R3. And then we want to examine how this is going to show up in an integral and what kind of integral it's going to show up. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. Remember, the truncated sphere problem is still an active problem. It could show up at any time to blow up your grade. I'm just kidding. Have a good day.